Thanks everyone for joining us this afternoon. Uh, Today we have Christine Brown with us to talk about manure. Christine is the Sustainability Specialist for the Field Crops Unit of the Ontario Ministry of Agriculture and Rural Affairs. Christine works with Ontario producers to address issues related to manure and nutrient management, organic amendment use, and maintaining and improving soil organic matter with the use of cover crops and organic amendments. She is the editor of publication 811, Agronomy Guide for Field Crops, and is a member of the OMAFRA soil team. Christine is a certified crop advisor with a 4R nutrient management specialty, and she lives on a small farm near London, Ontario. I also want to acknowledge that this workshop is a collaboration with the PEI Federation of Agriculture and the New Brunswick Soil and Crop Improvement Association through the On-Farm Climate Action Fund. And it is worth 1.5 points in nutrient management for the Certified Crop Advisor CEUs. And I'll provide the QR code in my presentation following Christine's, so you can get your hands on that. Thank you so much, Christine, for joining us today. And I look forward to hearing more about manure.
Well, thank you for the invite. It's always fun to talk with the, people in other areas and to learn a little bit about what happens in different parts of the country. So, I'll share my screen and then we'll get started. Can you see the screen all right?
Yep.
Okay. So I was asked to just give a little bit of an overview of manure management to improve nitrogen efficiency, soil health, and to reduce greenhouse gas emissions. Sounds like a lot for manure to do. And sometimes you think, okay, is manure the magic bullet? And maybe in some ways or sometimes it can be. Anyway, I'm going to start with the soil health portion of the presentation, and I just got to get, okay, there. And so when we talk about soil health, and we're always looking for achieving that ideal soil organic matter, the best soil we can, achieving a healthy soil, and we can get there with different practices. If we do just residue management, we can improve our organic matter. With cover crops, we can improve organic matter. Can you see my arrow if it's there? Okay. With the use of organic amendments, with crop rotation, and with reduced tillage. Each of those individually will benefit soil health. But if we do some of those practices together, we achieve that ideal soil organic matter level more quickly. And a healthy soil can help store more carbon and therefore reduce greenhouse gas emissions. In Ontario, we always look at the different soil textures, so a sand, a loam, and a clay. And ideally, we're going to be somewhere in that good to very good for organic matter levels. A lot of our soils in Ontario, we are definitely somewhere between the fair and the good, and have ways to go to try and improve those soil organic matter levels back to where they used to be. So organic amendments is where I'm going to focus today. But before we get there, achieving that healthy soil, there's a lot of different processes going on with the addition of organic amendments or with cover crops or with the combination. And the outcome that we're looking for is sustainable yields, resiliency, profits that we can count on with crop production. But there's a lot of invisible and dynamic processes that are happening below the soil. And we can see that when we start digging roots. We can see that in growth patterns. We can see that especially in dry times of the year where we've got water holding capacity that soils with less organic matter, with less resilience, don't seem to have. And so just because soil health is hard to measure, and it's hard to measure over a short term, I was looking at some studies, and this is a study by Richard Stenhauer from Penn State University that I found a couple of years ago, and I've broken it into a couple components. And so they started in about 1875 and broke some virgin soil and started growing continuous corn and did that for about 80 years and measured the soil organic matter level in that soil. And obviously makes common sense that organic matter level is going to go down, and it goes to a steady state after a number of years. Now, they also did in that study after that 80 years, they changed the management and added a corn, oats, clover rotation and added manure. And so after 50 years of that rotation compared to the corn rotation, we start to see a new steady state. We see an improvement in that soil organic matter level. But if we had done that rotation of corn, oats, clover with the manure right from the start, yes, the soil organic matter levels would still have decreased compared to the virgin soils, but never gone down as much as with the continuous corn rotation, and never as far down as when we changed the rotation and tried to improve our soil health. And so eventually, I guess if you did this long enough, these two bars would reach, or would match again, but it takes a long time. And I guess that's the point with this is that we can change our management, but we're not going to see those soil health improvements. We're going to see them, but they take time, and they may never be back to where the soil was when it was first broken or worked. And so another study, so that last one was looking at soil organic matter. This is one from the UK, where they added manure for 20 years. So from 1852 to 1871, they added 15 tons of manure every year, and then they stopped. And what I find really interesting with this is yields. So here they're looking at yields. And so even 100 years later, there's still a difference in the yields because they added, or I'm guessing because they added the manure those 20 years, almost 100 years ago. And again, it's not a big difference, but that there's any difference after 100 years was surprising to me. And then if we take that one step farther and we say, okay, they added the solid manure for the full, the 20 years on this purple line, but they kept adding that manure over time, you can see that the benefit in that grain yield from the nutrients from manure. But I still find it interesting that compared to unfertilized, we're still seeing that benefit that the manure added all those years later. And then if we look at the soil organic matter, same kind of thing. We still see that difference. And that's probably why we're still seeing that yield difference, is because we do have the increased soil organic matter, or organic carbon. And I think part of that is because we're feeding the microbial populations. Those microbial populations do more to add carbon to the soil than just the residue or just the carbon that's in the manure itself. So we did a topsoil sampling program across Ontario, and you can see in these green dots that locations were randomly picked by computer. And then we went to those sites and did some soil sampling on the upper, mid, and lower slope positions. And then we also did a management questionnaire to look at, okay, what was the rotation? What was the background in, like, is it livestock? Is there manure added? Those kind of things. And the only reason I'm showing you this is because we found some interesting things. And this is early time results, but where there was rotation, so where there were forages and perennials in that rotation, we had higher organic matter levels, as higher soil organic matter levels. That to me is not surprising, but that we have almost a full percentage in increased organic matter, I think is significant. And then the other one, and this one is more manure related, but where we had manure. And so in this survey, it doesn't ask how much manure or how often or what type of manure it is. It just says, have you applied manure or soil organic amendments? And where the answer is yes versus no, we have about 0.5% increase in that organic matter overall. And what that means, generally we can hold up to 15,000 gallons per acre more water. We have a higher nutrient content and higher cation exchange capacity. And so this kind of explains, along with the rotation, that improvement in resilience in the soil. And so this slide is just showing, I'm not going to go into a lot of detail, but we had a compost study a number of years ago. And this is one farm where he continued the application of compost once in rotation, so once every 3 years, and then left strips with checks. And in this visual from satellite image, you can really see the yellow strips are the check strips, And then the dark green and the dark blue, those are the different checks that, or not checks, but those are the different treatments we had with the compost. And it's really obvious that you can see the difference with where there was compost versus where there wasn't. And so it takes time. This is over a 10-year period. It takes time to see those improvements. But when we look at the yields, again, we can't look at it just 1 year at a time and say, yes, the compost is paid for itself. But if you look at 2018, where it was a dry season, a dry year, and because of that resilience, because of that additional moisture holding capacity, a 27 bushel yield increase in that corn. Is that going to happen every year? No, but we do have that resilience, and we see that in both the satellite image and in the yields. So I'm going to turn it now to more of the nutrients. And so manure is great. And in the years that I was first working with manure, it was all about the nutrients, not so much about the soil. I think now it's probably about half and half. But if we're trying to share information and improve the management of manure, a big part of it is talking about the nutrients, because it's the nutrients that people can see and can pay for. It's those soil benefits that are in addition to the value. So when, for example, in a fact sheet that we produce that's just been updated, we look at the lab analysis, and we get those lab analysis and aggregate that information from the labs. We use that and get an idea of what would be the available nutrients based on a specific dry matter. We've done it through dry matter ranges, but what this does is it says to growers or to people that are utilizing manure, gives an approximate value, fertilizer and PK equivalent. And so if people are selling their manure, they can say, yes, I'm willing to pay for all or part of the nitrogen, the phosphorus, and the potassium. And then as somebody that's purchasing that manure, I get that organic matter and the micronutrients as an extra benefit. Now, there's all kinds of ways that people sell manure, but looking at those nutrients is a big part of it. And so we have that both for liquid and for solid manure and for almost every type of livestock that you can think of. But we also have that in our AgriSuite tool. And I'm not going to go into this in any great detail because Mackenzie's going to talk about this later. But our manure calculator or organic amendment calculator, we basically can put in our analysis information either from a database or actual analysis that we have. And if we give the analysis information along with our timing for application and our incorporation details, so basically the management of that manure and our application rate, then we get an idea of what is the available nutrients for the following crop. We can also get an idea of the trace elements that have been applied. They might not be available, but those are what are applied based on the analysis. And we can get an economic value. So cost of application is subtracted from that, usable nitrogen, phosphorus, and potassium to give us an estimated value per acre. And they can be these are the defaults, but we can override them with actual costs. And so this is a quick way for people to really see what is the impact of management decisions with just a click of the button, and what is that value based on my management decisions. And we all know that fertilizer prices have increased in the past number of years. And this is a graph that I keep just of local fertilizer prices from just the local input dealer in the area I live in. And you can see that in the spring of 2021, those prices really jumped, and they're jumping up and down a little bit, but still pretty high. And so this, in combination with what we hear in the coffee shop, is leading to some really good opportunities for sharing. Okay, how can we do a better job managing the nutrients and especially the nitrogen in our crop production, and especially from the manure that we use? And so in the coffee shop, the conversation is the federal government is asking farmers to reduce nitrogen applications by 30%. That was in one of the publications, and that really grabbed people's attention. And so there's been some misconceptions with what the federal government has been asking, because in reality, they're asking, their goal is a 30% reduction in greenhouse gas emissions with the better management of nitrogen. And so there's a couple of things that I think are real opportunities. And instead of looking at it as a negative, it's if we can reduce the greenhouse gas emissions, but at the same time, we're making better economic use of our nitrogen, whether it's fertilizer or manure, that's dollars in our pocket. And so that's a benefit. And so in crop production, we ask, okay, how can we maximize commercial nitrogen efficiently for crop production? And so in Ontario, it's things like actually using the recommended nitrogen rates for crops by utilizing the credits. So if we use our corn nitrogen calculator, it'll say, here's your base based on your timing, based on the soil type you're on, based on credits like alfalfa or red clover, here's the amount that we recommend. And a lot of times when nitrogen isn't too expensive, people will use more than they actually are, than what is recommended, because they really like to see a dark green crop. So giving a credit to legumes can be anywhere from 30 to 100 pounds per acre. Giving the manure the credit, I'm going to get into that in a little bit more in a few slides, but that also can reduce the amount of nitrogen, commercial nitrogen that we're adding. Something as simple as injection or banding or incorporating the nitrogen quickly after application, as opposed to just surface broadcasting, can give us savings as much as 45% when the temperatures are hot, or about 10% or 7% when the conditions are cooler. And so broadcast application, obviously, if you're in wheat or cereals, you don't have a choice. But when the conditions are warm, so for corn, instead of putting that nitrogen with the herbicide, injecting it, banding it, incorporating it is going to give a savings. The other one is side dressing versus putting it all ahead. So if we put our nitrogen on in late April, early May, we may be putting on more than we need, because there's going to be some losses during that early season, as opposed to side dressing it in early June, where we might be able to save 15 to 20% of that nitrogen. And then the last one is the use of nitrogen inhibitors. This is relatively new, but depending on which ones you use, when it's used, and the weather conditions afterwards, we could get a savings as much as 40%. But that really does depend on the weather. So if we look at manure and maximizing that nitrogen efficiency with manure, again, using the nitrogen recommendations for the crops, especially for corn. So, and keeping those credits where we've got the manure. We can't give credits to manure if we don't test the manure. So we don't know where we're going if we don't have that background information. So testing manure is one thing, utilizing the fertilizer value of that manure within reason. Like there's nitrogen estimates are estimates. And so it really does depend on the weather. And so lots of people will give a little bit of a buffer to make sure that they've got enough. But the other part of this is if we add nitrogen or manure at the beginning of the season, and then we can come back if we don't have enough and side dress commercial nitrogen afterwards. The other one that doesn't get talked about a lot is, again, looking at those credits. But if we've got a solid manure, and especially a poultry or a broiler manure, where we've got pretty high organic nitrogen, that organic nitrogen has, part of it is available this year, but there will be some slow release nitrogen that is available next year and the year after and the year after. And so if we're applying manure every year, we could have up to 17% nitrogen savings just from those credits. The other one is the timing of that nitrogen application. Again, if we put all our nitrogen up front, or we side dress, and in this picture, we're seeing some manure being injected into standing corn. That's becoming more popular. With a drag hose, we can go over that corn up to 4-leaf stage without knocking it down and reducing the population too much. But we've also got equipment now that's starting to inject that manure into standing corn. And that's great if it's a pig manure or if it's an anaerobic digestate. If it's a dairy manure, we still would need some nitrogen up front, just because that combination of organic to ammonium nitrogen is going to mean a little bit slower release, depending on the type of manure that we're working with. And then the use of nitrogen inhibitors, I've got question marks. The nitrogen inhibitors generally last for about 3 weeks. And so we would have to time it really perfectly to see a return on investment, especially with the fall application, but even with spring application, it's so dependent on weather. So I think nitrogen inhibitors in manure is going to be tested, and we'll probably see some opportunities in the future. But currently, I think we're better to stick with the nitrogen inhibitors in commercial nitrogen. And so there's other management considerations that will help with not just the nitrogen, but the nutrients. First of all is, again, that economical nutrient utilization through the right rates, and the right timing and the right placement, of course. Combination of manure with diverse rotation like alfalfa or forages and or with cover crops. And in Ontario, even wheat has a big benefit in improving that yield over the rotation. Using the 4R approach means that we're going to minimize the environmental risk of contamination, especially with phosphorus, but also with nitrogen and some of those greenhouse gas emissions. And really, if we're talking about the greenhouse gas emissions, targeting that manure application to growing crops is probably the best thing we can do to reduce the nitrous oxide emissions and some of the other emissions that we get. Some of the other considerations: uniformity of application. Calibration is extremely important. Calibration both in rate, but calibration in uniformity over that whole width of spread. If we have a storage where we've got high water content, so a lot of the hog operations in Ontario will have 2-3% dry matter, which means 98-97% water. Over the time of that storage being in place, that's a lot of expense in transporting water to a field. So anything we can do to reduce that water content of the liquid manure, keeping the rainwater out, keeping the wash water from the cleaning out, going through a screw press, any of those kind of things will help improve the solids, but will also concentrate the nutrients that we're taking to the field a little bit better. Manure into growing crops is a great idea. Do we have the equipment? Is that equipment? That equipment is coming. There's a lot of it in Europe that's starting to make its way to Ontario and to Canada. But that's expensive and it takes some time. And then the soil health and compaction, a big part of it. We're getting a lot more information about compaction and what we can do with tires and with inflation deflation systems to make a big improvement in that. And then there's also the use of other tools like the Harvest 3000 that does the manure sensing on the go and can help to improve that consistency in rate for nitrogen or for phosphorus or whatever our target is. And then, of course, the tools like AgriSuite that we have in Ontario. And just to show again, and I'm going to talk more about nutrients, but here's a cover crop with manure on the right-hand side, and then without manure on the left-hand side. And so just looking at the increase in that carbon content, in that biomass, and what we're looking at here really is when we apply that manure, and in this case, it was liquid manure, which is going to act faster on these cover crops than a solid manure would, but we're feeding the microorganisms in the soil. Those microorganisms are active or most active around the root systems of these cover crops. And so they are getting the carbon from photosynthesis and from the crop, and in exchange getting the nutrients. And so we're seeing that increase in that biomass, both in the top growth and in the root growth. And that really helps with that carbon storage. And so in this picture, how much carbon is being stored? Obviously, there's a lot of nutrients being held and carbon being stored here. The question is, how long? How do we know when that nitrogen or when that carbon is released again? And so manure is complex. And this is also a complex slide. And I found last week when we presented some of this information, we could have spent the whole time just on this slide. This is a conceptual drawing. I'm just going to emphasize it's conceptual based on a bunch of different results, study results, and then also what we see. And so the solid lines represent, the green line is red clover, the yellow line is oilseed radish or daikon radish, the blue line is oats or barley in vegetative state, and then the orangey red line is cereal rye where it's headed. And so the solid lines are the cover crop without manure, and then the dotted lines are the cover crop with manure. And so what we're trying to show here is it's really difficult to decide exactly when the cover crops and that nitrogen from manure is going to be available to that crop, because it's impacted by so many different things. It is impacted by weather, so temperature and moisture, and that's probably the biggest one. By soil organic matter, and what is the soil health already? Is there a lot of organic matter? Is there a lot of microbial activity in that soil? What was the previous crop? What is the cover crop? So these different cover crops will have different release rates for both the carbon and for the nutrients. Carbon to nitrogen ratio is a big one, and that's especially if you're comparing the vegetative oats and barley versus the cereal rye that's been headed, just because you've got more cellulose, more lignin in that cover crop. Where you've got manure added, you've got more nitrogen in that cover crop, so that's going to reduce the carbon to nitrogen ratio a little bit and affect that availability. So cover crops can hold on to the nutrients to prevent losses, but it's really difficult to know exactly when they get released and how that manure will affect that release. But needless to say, if we look at the corn requirement, and this is, I'm guessing this would be true in the Maritimes as well as in Ontario, but basically the corn grows the fastest from that 6-leaf stage to tasseling. In Ontario, that's generally from early mid-June to late July, August. And so red clover is the cover crop that fits that nitrogen need and that nitrogen credit the best. The other cover crops will give us some benefit. It's hard to say exactly how much, and it's not going to replace all the nitrogen that we need in our cover crops. And so this is just a slide that shows the growth of corn and when that corn nitrogen, not only nitrogen, phosphorus and potassium as well, when that need is the highest. But our goal with manure and with cover crops as well, but especially with manure, is to have the highest nitrogen availability during that period when the corn fertilizer needs are the highest. And so that's easiest with manures like anaerobic digestate or pig manures. It's a little bit harder with dairy manures, with beef manures, where we've got pretty high solids, and a lot of that, the composition is about 50% ammonium, 50% organic nitrogen. And so it's hard to have it all available right here. We usually do need some additional commercial nitrogen. And so the AgriSuite calculators, like I said, I'm not going to spend a lot of time here, but they are available to anybody. They're free. You just go to the AgriSuite omafra.gov.on.ca. And there's several of these calculators that it doesn't matter where you are. You can be in the States, you can be in Ontario. They do have some usefulness. There's some that are a little bit more site specific. They're available in French and English, in metric, imperial, and US units. You can change them on the go, and it's available for computer, tablet, and for phone. And so the crop nutrient calculator looks at the soil test values, but also crop removal, and gives an idea of what is your crop needs based on the crop and your yield goals. The organic amendment calculator gives you an idea of the available nutrients based on analysis and management. Fertilizer calculator, you can do some blending to achieve target fertilizer rates or to add additional. Phosphorus loss assessment determines the risk of phosphorus loss from various management practice. So it's a really good tool to say, okay, how much difference does it make if I apply manure in winter compared to in the spring, and incorporate it, that kind of thing. Field management tool incorporates all of these above tools to give a nutrient balance over a whole rotation. So I can put in my corn, my soybean, my wheat crops into that rotation, where I'm applying manure, where I'm applying fertilizer, and at the end of that rotation, get an idea of what is my nutrient balance. Am I short nutrients? Am I over applying nutrients? Where do I need to add more or to add less, based on where my soil test levels are? Then there's the manure storage and sizing. This one it can be used anywhere, estimates manure production, storage volume requirements, and the nutrient content using all the different common livestock in the housing types, and then also anaerobic digestion, composting, and those kind of treatments. And then the newest one is our greenhouse gas calculator, which estimates greenhouse gas emissions. And I'm going to get into this in a little bit more detail. So this is the crop nutrient calculator. I'm not going to spend any time on it because it's more specific for Ontario, but it does give the crop removal, which I think would be relevant anywhere. This is again a screen from the organic amendment or the manure calculator. Again, it gives you the available nutrients, and it gives you the value based on some specific management practices. What it lets you do really quickly is if I take that average dairy manure and I try, okay, what is, if I pick spring, if I pick fall, if I pick late summer with a cover crop, without a cover crop, and I pick different incorporation times, what does that mean? So at a click of a button, I can see the impact that different management has and different timings have on my available nutrients and on my value. This is a screen of the field, the field management plan. So I've got my corn crop, my soybean crop, my wheat crop with the different manures that I might be using and my starter fertilizers or nitrogens that I've been adding. And so at the end of it gives me, and based on the, I can use crop removal, I can use my nutrient needs or the regular one, or I can take a hybrid where it looks at the nitrogen recommendations and then the removal for phosphorus and potassium, and gives me an idea. So in this example, I'm short on my potassium, and that is quite normal with the field management plan where we use manure. We often don't add enough potassium in that rotation. So I'm going to spend the rest of the time on the greenhouse gas part of it, not all on the AgriSuite, but AgriSuite greenhouse gas calculator is a tool. It's an education tool, and it really looks at the management practices that impact greenhouse gas emissions, and especially those right on the farm. So this is very specific to a location like a farm. It also helps us to better understand the differences between the carbon, the methane, and the nitrous oxide losses and where each of those occur. And really, we can look at what kind of differences are we already making in reducing emissions based on some of the practices that we're doing in our livestock and crop production systems. So the greenhouse gas results, and I'm borrowing some slides from James Dick. He's our engineer that's been doing a lot of the work in AgriSuite on the greenhouse gas calculator, him and Amadou T. So this is the bar that you see when you go through the calculations. And so you get a baseline, and then you get a line on your mitigations based on the practices. And we can specify specific practices. We can see the details of those practices. We can also do some of these in the actual, when we put our information into the field crop part of it or the livestock part of it. And so we've got 3 different gases that we're talking about. And when we talk about the greenhouse gas emissions, we're talking about CO2 equivalents, or basically putting them all into an apples to apples comparison. But it's important to know that carbon is the equivalent of 1. Methane would be 28 times that of the carbon dioxide, and the nitrous oxide significantly more than that. And so that's why we do look at those different gases and where they're occurring. So in Ontario, and so this is, I'm not going to spend a lot of time on it. I suspect it will be similar in the Maritimes, but the total emissions are about 150 megatons of CO2 equivalents. This represents 8% represents the part that agriculture plays. And that's not totally true, because there would be some in the energy part of it as well. But generally, that's what's reported for agriculture. And of that total, 83% is carbon dioxide. And of that, agriculture represents 2% of that. In Ontario, 9% of this total emissions is as methane, but of that 9% total, 34% of that comes from agriculture. And that's where manure is probably the biggest one, the livestock manure. Nitrous oxide is only 5% of that total emissions total, but of that 5%, 69% of that comes from agriculture, and a lot of that is in the fertilizer use and the nitrous oxide emissions from the soil and fertilizer use, and manure is part of that as well. So the tool in AgriSuite is really looking just at the farm unit. And so it's looking at the livestock at the fields, so where the cropping is occurring, and then at some of the buildings. And some of the buildings would be the barn, would be the grain dryers, it would be greenhouses where you're growing greenhouse vegetables. And so beneficial management practices, we've got a bunch of them, and I'm going to go through some of them, obviously not all of them. I'm going to cover some of the manure ones, because I think these are slides that I borrowed from James, and I found them really, really interesting. And I hope you do too. So anaerobic digestion is a big one that talks about reducing the methane losses by capturing them for energy. And this is a complicated slide. And the only thing I'm going to say is that in AgriSuite, it's really just the anaerobic digestate that we're talking about. So if you look at the methane reduction, it can be as much as about 60%. However, the nitrous oxide emissions from that digestate applied to the soil can vary depending on the timing and the rate and what the pH level of that digestate is. Another practice that's relatively, I won't say it's common, but it's gaining more interest, and it's looking at separating the solids from the liquids. And in a lot of cases, that's using something like a screw press. But it's also looking at other options. In some cases, it's anaerobic digestion where they're separating solids out afterwards. Anyway, where they separate that solids, there's a big difference just because of the solids that we're starting with. With dairy manure, we might see a methane reduction from separating the solids as much as 50%. With swine manure, or digestate, it would be significantly less, just because we're starting with quite a bit less solids in that manure to start with. Covering a liquid storage with straw. So if we're talking about 6 inches of straw, that straw suddenly creates an environment where the oxygen from methane, they can break down some of that methane. They can't be released from, that methane isn't released the same as if you've got no crust or no covering. And the reduction can be as much as 15%. This is one that I found really interesting, and this is work that Claudia Wagner-Riddle and others did, but where they were looking at when is that methane released from a storage, and does timing of emptying that storage make a difference? And so in this graph, you can see that the highest amount of, the highest amount of losses come during those summer months when it's warm. We have high ammonia losses. We also have some methane. And so if we empty that storage first thing in the spring, it takes some time before those conditions get anaerobic and before we've got the microorganisms that contribute to that methane loss. And so we can, if we empty it partway through the summer, same kind of thing, it takes time for that methane to get there again. And then you can see that if we empty it in the spring and we empty it again in the fall, we get the maximum benefit. So we might get a reduction as much as 40% or 25 to 40%, depending on when we empty that storage. But emptying it just in the fall is probably going to have the highest amount of those methane losses. Acidification is something that we're starting to hear more about, both from the manure and from the manure going on to the field with the tanker. Now, with the tanker, that's mostly still being tested in Europe, but there is work being done at Agriculture and Agri-Food Canada. Andrew van der Zeg in particular is doing some of this work. Now, typical manure, James has said that the typical manure is between 8 and 12. Any of the manure that we've tested, the typical range with liquid manure is anywhere from 6.5 to 8.5. I haven't seen many that are much above that. Anaerobic digestate, pig manures, those tend to be in the higher 7.8 to 8.5. Solid manure, almost all the solid manure is in that 8 to 8.5. Our goal is to get that pH, I'm going to say probably closer to 6.5. getting that pH to 5 would reduce the emissions, but would be very, very expensive. And so this is not, the acidification has not been tested with economics as much yet. But if we can acidify it to somewhere between that 5 and 6.5 range, we can reduce our emissions by about 40%. And that's pretty significant. Composting manure. So composting manure, most of you will know the process. We start with raw manure. We have heat, we have moisture, we have some gases that are lost from the system, because that also reduces the volume. So we end up with a finished compost. We've probably, depending on how good a job we've done, lost carbon dioxide, some methane, and maybe some nitrous oxide as well. So how much we reduce the methane reduction depends a little bit on the process. And it also, how much nitrous oxide emissions we lose depends on that process. So I think there's still some work to be done here to figure out what is that process and how much difference can it make. But the compost itself, once it's a finished product, then your management for nitrogen and phosphorus emissions are much, much lower. So I'm going to go through, I have about a few minutes left, so I'm just going to go through a really quick farm example using the AgriSuite tool. And so we're using 500 acres of crop production, and we used a real live farm for this example. Livestock, 120 milking cows, and buildings, a grain dryer, and then 2,500 tons of corn dried annually. And I'm going to say right up front, I am not an expert on grain dryers, and so those numbers come specifically from James. But the fields, we had a corn, soybean, wheat rotation, conventional tillage. So we're going back to the conventional practices that we started with about 10 years ago. The fertilizer was broadcast. The nitrogen was applied a little bit in the starter, and then the rest of it was applied with the herbicide. So it was surface applied. Wheat, the straw was removed, but no cover crop. So those are conventional practices where we use the AgriSuite tool, and it does depend a little bit on where you are in the province, but about 766 tons of carbon equivalent per year. Where we did some additional BMPs, or we did all the BMPs we could think of. So corn, soybean, wheat rotation, where we had a cover crop it was covered every year going into the winter. No-till for corn, soybeans, and wheat. The no-till in the corn was might have a little bit of zone till depending on the year. Fertilizer, we looked at all the legume credits. We looked at timing so that we could side dress some of that nitrogen and reduce the amount we needed. We took the credits from manure that was applied. So we applied some digestate and some compost. And then we had, like I said before, the cover crop after wheat, and then cereal rye after corn. And then the wheat is a cover crop over the winter. And then the other thing we did was establish a 20-acre woodlot with mixed species. And so based on our conventional, we reduced our carbon equivalent by about 88%. So from 766 to 92 tons per year. If I wanted to get it to carbon neutral, we would have to plant a few more trees or look at some other practices like nitrogen inhibitors or some of those kind of things. So this is what it looks like. I've got my corn crop, I've got my soybean crop, my winter wheat crop, similar to what we had in the field management tool. And then I can look at my base scale. I've gone from my baseline to, I've mitigated to, to quite a bit less. And then this is if I press the information button, the additional details, I can see where I'm storing carbon from that cover crop. I can see where I'm potentially losing a little bit from the nitrogen use. And so these are the kind of screens that you would see when you're using the tool. With the livestock conventional practices, I'm looking at just normal feeding. I'm looking at a liquid manure system, and the manure is all spread in the fall. And so I'm looking at about 1,650 tons of carbon equivalent per year. Now, if I add some BMPs, and I'm not adding all of them, I could do more, but feed additives so that there's 2% dietary fat for the milkers, and I'm optimizing my diet, liquid manure with an anaerobic digester, I've got a straw cover, and I'm applying that manure both in the spring and in the fall. So there I'm looking at a 39% reduction in that carbon emissions. If I have grain dryer system, continuous flow with propane fuel, 2,500 tons at 25% moisture, dried to 15%, and I'm immediately cooling in the dryer, I can get about 111 tons of carbon equivalents, which is equivalent to about 73,400 liters of propane. If I use some BMPs like continuous flow, propane burner, optimized burner for fuel to air ratio, heat recovery system installed, same with the moisture and dry to 15%, but I'm delaying the cooling, dryation in the bin. So I'm reducing about 37% to about 70 tons per year. Now, obviously not every farm is going to do everything, but where we compare it to our baseline. So in our baseline emissions, we had the orange represents the amount from the livestock lost through mostly methane. The crops was mostly through nitrous oxide emissions, and the dryer, we had a 5% loss. So when we look at adding some of those BMPs, then we have reduced those losses significantly, and basically reduced the emissions by about 54% over that one site. So it sounds like a lot when we're being asked to reduce emissions by 30%, but I would say in a lot of cases, the baseline that they're using in Ontario is 2005. And if we look at the amount of cover crops and we look at a number of the best management practices that have improved since then I think that target over the whole province is quite doable. So just to summarize, some of the BMPs that help to reduce greenhouse gas emissions, crop rotation with cover crops. So ideally, if we can keep the soil covered over winter, if we're looking at more perennials, more legumes in that rotation, that will help with storing carbon, especially splitting the nitrogen so that we apply the nitrogen, some nitrogen up front to make sure that there's enough there for the crops, but then go back in and potentially side dress the additional nitrogen that might be needed. And that's especially important when you look at the differences in weather from season to season. If I have a warm spring and those microorganisms in the soil start to work earlier in the spring, I usually get a higher amount of nitrogen available from my manure, from my cover crops, than if it's a cold backward spring. And so if it's a cold backward spring, we can do the side dress nitrogen test and get an idea of how much additional do we need to add. But if we've got enough, we might be able to save the trip. So overwintering cover crops, I think I already said that. Applying organic amendments, we can replace the fertilizer, add some carbon. Where we apply those amendments during the growing season, we can, especially after wheat with cover crops, but we can maximize the efficiency of those nutrients, reduce the losses, and especially reduce some of those phosphorus and potential greenhouse gas losses. Solid manure, I know that liquid manure is more efficient in a lot of cases, but solid manure can have its benefits too, because especially as we look at potentially selling manure off the farm, transporting manure from areas of high fertility to areas of low fertility, solid manure can travel a much bigger distance than the liquid manure, especially when it's high water volume. Manure storages, emptying them more frequently, covers for liquid storages, acidification, anaerobic digesters. And I'm even going to go one step further and say intermittent aeration might be another way of not having the methane losses and potentially treating that liquid storage a little bit more like a compost pile. There's still research going on that, but I think that has some potential as well. And then, of course, establishing woodlots, windbreaks, buffers, so that we capture some of that carbon over the longer term. So with that, I'm going to ask if there's any questions, and thank you for taking the time to listen to this.
That was great, Christine. Thanks so much.
Do you want me to stop sharing the screen?
You could leave it up while we go through the questions. just if anyone wanted to take any of your contact information. So we've got a few questions here. The first one, okay, those recommended, and this might have been from towards the beginning of the presentation, those recommended soil organic matter content levels are based on tests using LOI, loss on ignition method.
Yep.
Okay. You had mentioned using something like a screw press to separate out the liquid of the manure so that you don't have to truck as much volume to the field for application. What are producers doing with the liquid?
That's a really good question. So a lot of them, and this is going to have more opportunities as the technology gets a little bit better. But you saw the picture of the cadman that was applying manure into standing corn. If we have really liquidy manure, so the solids have been screw pressed off, and you've got less than 1% dry matter left. You can take that and apply it to alfalfa fields or to corn. And on years where you've got drought type conditions, dry conditions, there's always somewhere where it's dry in the province, at least. We can provide some water, and a lot of times adding some water with some nutrients is doing more for yield than anything else, just because it's dry at that time of the year. So it's not, like I said before, transporting water is expensive. So if we've got a drag hose type system, there's some systems coming in place where you've got robotics that are potentially moving a drag hose slowly through the field. I think they're called V something. I forget the name, but there's they use K-lines. They're using K-lines a lot in Australia and in some of the other areas where it's dry. And so it's on a kind of on a line, almost like a boom, and it moves slowly through the field. And it's basically just giving you very watery manure with just a little bit of nutrients. So it's not easy, but that's where I see we could use those liquids.
Okay, great. Why does acidifying manure reduce emissions? In Nova Scotia, we often have acidic soils. Is acidifying the manure going to decrease soil pH even more once applied?
Yeah, that's a good question. We don't suffer from a lot of acidic soils in Ontario. If anything, we've got calcareous soils, and so that's a question we get a lot. Yeah, acidifying the manure in the storage, I don't think is going to make a big difference in what happens in the field. Acidifying the manure with the tanker as it's being applied, like they're doing in Europe right now, that one I would want to do more studies on before I tried it, because it really comes down to what is the buffer pH of the soil. And so if your buffer pH is close to 7, then that acidic zone isn't going to last very long. But if you've got low buffer pH, then potentially it could have a negative impact. And so I'd want to test that before doing that on a large scale on soils that are acidic.
Okay, great. So do you have suggestions for reducing greenhouse gases from manure applications on forages where incorporation is impossible?
Right. So that's a really good question. And the biggest loss you're going to get from putting manure on alfalfa, which I'm a really big fan of, because it really does make a yield difference and you're getting some of that moisture. But so I'm going to give a little bit of a comparison, and I was going to talk about this with the anaerobic digestate. If we apply that manure in late fall, let's say after corn harvest or after soybean harvest, but in Ontario, a lot of manure gets applied in that mid to late November, sometimes December time period, especially if it's a wet year. And so we've got liquid manure, high rates, and they're basically there because it's the ammonium, the temperatures are cold enough, the ammonium doesn't volatilize the same. It doesn't transfer over to nitrate as quickly, so it stays in ammonium form until spring. But then if we've got that pool of nitrogen sitting in the soil and we get cool, wet conditions in the spring, those are the conditions where nitrous oxide emissions are the highest. So I think that, I don't know even if they've been measured or how much, and I think it probably depends on the year. But if we're applying that same liquid manure after a forage cut, as soon as possible after we harvest that forage field, that nitrogen, we're going to lose some ammonium, but it's not going to be the nitrous oxide because first of all, it's being applied to a growing crop. The microorganisms are there. There's going to probably be a crop canopy there very quickly. So the microorganisms and the systems that are occurring in the soil are really helping to reduce the losses. Now, there will be some ammonium loss, but I think that the nitrous oxide emissions will actually be quite a bit less. And I'm not an expert on those numbers, but that's just the overall concept I see. The more we can do to incorporate, to apply manure into growing crops, not incorporate, but incorporate that practice so that we're applying them into growing crops, I think from a greenhouse gas emissions means that we're going to have less emissions.
Okay, awesome. So it seems that phosphorus recommendations around the world are being drastically reduced. How are these recommendations reconciled in Canada when recognizing the benefits to nitrogen, but the potential buildup of phosphorus?
Yeah, that's a very good question. So again, there's technology that I think is going to have a benefit for this. So when we talk about technology like Harvest 3000, where it's measuring the phosphorus in the manure, now how it has to be calibrated, of course, and it's not as simple as just plugging in a number. But if we're maintaining the level of phosphorus with application, for example, we are not going to be able to apply enough nitrogen to meet the corn, well, especially if it's corn. It depends on what crop, of course. So there's people that are looking at, okay, we can track what we've applied from manure. And so we can go back with GPS or with site-specific technology and apply the nitrogen that we need where we didn't apply enough ahead of time. And if we have variable rate technology to say, here's how much nitrogen I need in my high management zone versus my low management zone, I can even change that commercial nitrogen rate. The other thing that some people are doing is they are adding commercial nitrogen right into the manure tanker. And so that they're applying it in one trip. That they're doing that in Ohio. I haven't seen a lot of that happening in Ontario yet. But those are some of the things. The other thing that I think we will see more of in the future, I'm not sure about the Maritimes, but I'm guessing, is as we get more nutrients from urban sources, and if they're composted, then some of the, in other words, if organic matter becomes a commodity the same as phosphorus and nitrogen does, then we might have the opportunity at some point to have organic matter compost, in this case, stored with outlets, with fertilizer outlets, where they might be able to take some of that compost, mix it with fertilizer, so that when the cereals are harvested and they're going to put in a cover crop with and add some of the nutrients based on 4R, so right time, right place, they might be able to mix some of that organic matter that has the phosphorus and then fine tune the phosphorus and then add nitrogen for their in crop. So there's a bunch of different strategies, and I'm talking futuristic here, but I think that some of those combinations are things that we'll see to fine tune that nitrogen management without over applying phosphorus, because that is a big problem.
I've got one more question here. Oh, no, there's a couple. So you had a slide showing compost gave higher yield. I assume this was composted manure. I think that's what they meant to write.
Yeah, no, and actually that wasn't composted manure, because that was a study that we did with green bin. And so that compost that went to that site was actually it was leaf yard waste mixed with some food waste. And it was probably less available than manure compost would be. We tried it at 10 tons and 20 tons. Definitely we found out that, yeah, we might be adding more carbon at the 20 ton, but from a yield and from an economics perspective, the 10 ton was enough. And that's one of the things that we're finding out with compost a lot of times is that I'm not going to say less is better, but we can look at the economics, and 5 tons will do the same kind of things for the soil as 10 tons will. Maybe not from a nutrient perspective, but from a soil health perspective.
So this question had a couple parts. So the next part of it was red clover releases nitrogen at about the max demand period for corn. Was this fall planted and spring tilled?
That's a good question too. So most of the red clover gets frost seeded in the spring on our wheat crops. And the problem with the red clover is you don't always get a nice uniform stand, especially if you've got really good yields. So some people will go back in and they will spread some crimson clover into it, or they'll spread some other cover crops into it because the clover itself isn't uniform. But so the spring tilled, the difference in nitrogen release will be more on when that clover is terminated, whether it's terminated in the fall or whether it's terminated in the spring. It doesn't make a big difference if it's plowed in or if herbicide is used to kill it. It's more timing, and usually the fall, because you're tilling it in the fall, and again, it depends on weather, depends on how warm it is. But once your soil temperatures get lower than 10 degrees, the soil microbial activity slows down, and so you're not going to get much of a release, but you will have a head start on the spring. So the release from a worked or fall terminated is going to be a little bit ahead, most of the time, than a spring tilled, unless it's really warm conditions or abnormally warm spring. But I don't know the exact numbers, and it's often weather related, but there is a little bit of a difference. And the graph, that information came from Bill Dean. I took a bunch of different studies, but Bill Dean did the most amount of work looking at that. And if people want that information, send me an email and I can send it to you.
So do you recommend liquid manure application to alfalfa for establishment and for maintenance?
Not for establishment. We did a study. I didn't have the guts to do it, but a farmer that did. We did an establishment study. Ahead of establishment is great. Like if you're putting the manure down and then you're establishing the alfalfa, that's fine. But if you've established it and then you want to put manure on to that small crop, I would not recommend that. Once you're into your full production year, yes. And the reason is that in that initial stand, every plant represents a crown. You don't have crowns yet. So every plant is going to produce a crown. So if you damage that plant before it's really had a chance to produce that crown or to make that crown, to have that root system in place, then anytime you have wheel track damage or if the application isn't uniform enough, you're going to have either too much nitrogen burning potentially, or you're going to have wheel track damage, and then those plants aren't going to survive as well. So I would say manure on alfalfa is great, but more after your first production year. And you can do it after every cut if the weather allows. And it depends on your nutrients, of course. You don't want to apply too many nutrients. But generally, you cannot add the amount of potash that's being removed if you've got a 3 or 4 cut system. We have quite a few guys in Ontario that do 4 cuts. That's pretty hard on the crop, and it removes a lot of nutrients.
Okay. I think that's all the time we have left now for questions. So thanks again so much, Christine. That was a great presentation. And I noticed a couple comments in the chat. People were already looking forward to looking at the recording. So thanks so much.
No, thanks for the invitation.
And yeah, feel free to stick around if you would like, Christine. I'm going to go through some manure calculations now. So I'll share my screen. And can you see that all right?
Yep, you're not in presentation.
Okay, great. So yeah, my name again is Mackenzie Rathgeber. I'm the Agri-Environmental Specialist with Perennia Food and Agriculture. And there is the QR code that I promised there on the screen if you wanted to snag it. So before I get into the calculation side of things, I just want to reinforce why we're talking about this in the first place. So manure is a resource, as this is just going to be all of, maybe a little bit of repetition of what Christine has already gone over, but yeah, manure is a resource, and with proper management and utilization, you can offset fertilizer costs and improve your environmental stewardship in the process. Manure is rich with nutrients important for plant growth, notably nitrogen. And if the nutrients in manure are not utilized, they are otherwise lost to the environment through groundwater or surface water leaching or volatilization. And additionally, the incorporation of manure into the soil is a valuable source of organic matter, which can help build soil health. So how much nutrients am I getting from my manure? There are 3 basic steps in estimating the nutrients that will be available from an animal production system. First, you need to know how much mass or volume of manure that you're going to be dealing with. And then you're going to need to know the nutrient content of the manure. And then most importantly, you need to know what's going to be available from that nutrient content to your crop following land application. Mass or volume of manure produced can be estimated by either direct measurement of manure, estimation of your storage volume, or simply based on animal numbers. Here you can see some book values that you could refer to. And as you can see, a lactating cow on average would produce a bit more manure than, say, a dry cow. So once you have a reasonable estimate of how much manure you're going to have, the next step is to estimate the nutrient content of your manure. Direct measures of nutrient composition through manure sampling and analysis are always advised, as they will provide the most accurate estimation of nutrient content. However, if these are not available, as the previous slide showed, you can use book values. So here, again, you can see that a lactating cow on average would produce more nitrogen in manure than, say, a dry cow. And here I have on the screen just a lab analysis of semi-solid poultry manure. And we're going to use this example in our first calculation. So dig out your calculator or bring it up on your phone if you can. So on Charlie McDonald's farm of 12,000 layers, manure is managed as semi-solid. So I clipped that previous analysis just for the purpose of this example so that you can see it more clearly. If we know approximately 420,480 kilograms of manure is being produced per year, how much total nitrogen per kilogram will be produced per year, and how much ammonium nitrogen will be produced per year? Oh. So I'm going to bring up a poll and you can take a shot at that. Did the poll pop up for you?
Not yet.
Okay.
There we go.
Okay. So I'll just give you a second there to figure that one out. Hopefully I didn't spoil it by Okay, so I'll share part A. I see some more. And now I'm going to bring up part B, and you can take a shot at that one. Okay, so now I will reveal the results. So to figure out the total nitrogen, you would take, as you can see here on the analysis, as received, because you would be applying your manure would be as received, and you wouldn't be having a dry manure unless you were drying your manure. Actually, I guess I should have specified that, but you would be multiplying that by 1.55%. So you would have about 6,517 kilograms of total nitrogen. And then similarly for ammonium, it was 0.28%, giving you 1,177 kilograms of ammonium N. So another example, Susan Kelly, a vegetable farmer, wants to spread some of Charlie McDonald's poultry manure on her 20-acre or 8-hectare field. If she spreads at a rate of 4 tons per acre, how much ammonium nitrogen is being put on her acre? Being put on per acre, sorry. So just a reminder, since the analysis isn't sitting there anymore, the percent ammonium nitrogen reported in the manure analysis report as received is 0.28%. And if we're spreading at 4 tons per acre, that is about 8,000 pounds of manure per acre. So I'll let you take a shot at how much ammonium nitrogen would she be spreading. Okay, I'm going to end it there. So you're going to multiply that 8,000 pounds of manure per acre by the 0.28%. So she'd be spreading about 22.4 pounds of ammonium nitrogen per acre, or if you like to think in kilograms per hectare, it would be 25.1 kilograms of ammonium nitrogen per hectare. However, depending on timing and method of incorporation, the amount of this ammonium nitrogen available to the crops will vary. So I'm going to get into that. So we've reviewed ways so first step is estimating the mass volume of manure from a system. Then you need to know or estimate the nutrient content of your manure. But lastly, which is sort of the critical piece of this, you need to know how much is actually going to be available for your plant. Specifically, we're going to cover nitrogen. So nitrogen exists within several pools in the soil, and nitrogen will vary within these forms and pools. So estimations need to account for this. So ammonium nitrogen and organic nitrogen differ in their availability and should be calculated separately. Ammonium nitrogen is immediately available to plants after land application, but also can be easily lost to volatilization if it's not incorporated and remains on the soil surface. And the longer you wait to incorporate, the more you're going to lose. Ammonium nitrogen is almost immediately converted to nitrate and then is taken up by your crop, or it can be lost through leaching if your soil is waterlogged or compacted, as you can see in the diagram here. And organic nitrogen, which is a large component of your manure, is not immediately available to plants. It's highly dependent on the activity of the soil microbes. So your microbes need to mineralize this nitrogen into ammonium nitrogen, nitrate, or they also can immobilize your nitrogen. So if you have a high carbon to nitrogen ratio, so not a whole lot of nitrogen in your manure, those microbes will use up all of that nitrogen and you may not actually have any plant available nitrogen for some time. So manure application in the spring or summer will decrease volatilization nitrogen losses compared to fall application. And as I mentioned, immediate incorporation will significantly decrease your volatilization losses compared to delayed or non-incorporated manure, excuse me. So here I've got a couple arrows pointing. So if you look here at this liquid dairy or other livestock manure that is less than 5% dry matter, if you liquid inject this, so it's immediately incorporated or within the hour, you're going to retain about 95% of that ammonium nitrogen. But if you don't incorporate or wait more than 7 days, then you're only going to retain about 60%. And then looking at fall application, so again, if you have that less than 5% dry matter liquid dairy and you immediately incorporate or inject that, you're going to retain about 40% of that ammonium nitrogen. And then if you don't incorporate or wait more than 7 days, then you will only retain about 25% of that nitrogen. So, which brings me to another example. Now we're going to look at not only the nutrient content, but the nutrient availability. So a farmer is planting the field behind the barn to cordon silage, which is about 20 acres or 8.1 hectares. According to the local lab, the nitrogen requirements of silage corn are 115 kilograms per hectare or 102 pounds per acre. The producer plans to inject liquid dairy manure pre-plant in the spring with a manure analysis reporting a value of 9.58% dry matter, 0.31% as received total nitrogen, 0.13% as received ammonium nitrogen, and a carbon to nitrogen ratio of 14.3. If they plan to apply 50 kilograms of nitrogen per hectare at side dress, how much manure should they put on pre-plant on the field behind the barn? So to solve this problem, first, you'd need to determine the amount of ammonium nitrogen that is plant available based on your application timing and your incorporation. Secondly, you need to determine the amount of organic nitrogen that will be plant available in the first year of planting. So what's going to be mineralized. You can also calculate what will be available in year 2 and 3, but I didn't include that in this equation, in this example, but it's pretty straightforward how you do that. Once we get there, you'll see. And lastly, then you can determine the rate or amount of manure needed for pre-plant. So that brings me to the first part. So first we need to determine the amount of ammonium nitrogen that is plant available based on application timing and incorporation. So we know we have a 0.13% ammonium nitrogen. To calculate that by weight, we would multiply by 10 and we would get 1.3 kilograms per ton, or if you wanted to know pounds per ton, it would be 2.6 pounds per ton. And because this is liquid manure, we're going to calculate it by volume. So that would give us 1.3 kilograms per 1,000 liters, or 11.1 pounds per 1,000 gallons. So to determine the amount of ammonium nitrogen that is plant available based on application timing and incorporation, this is the information we know, and this is sort of the guideline to how much you're going to retain. So to determine the amount of plant available nitrogen in the liquid manure, you would apply the volume by the appropriate percentage available shown in the table. So we know we have 1.3 kilograms per 1,000 liters, or 1.1 pounds per 1,000 gallons. We know it's spring applied, and we know it is a 9.58% dry matter. So I'm gonna bring up the poll here and let you take a shot at it.
Mackenzie, there's a question in the chat there about whether you should always ask the lab for ammonium N testing. It says in PEI, the lab has a manure compost test option with only total N. I see Christine's typing an answer, but what are your thoughts on that?
I think it's, let me just read that question.
Like, to me, like if you want to be calculating how much N is plant available at time of application, ammonium N is a very useful number to have.
Yeah.
Can I answer that too?
Yes, please.
I would always ask for an ammonium regardless, even if it's a compost sample. And the reason for that is it's good to know what the ammonium content is. It's also good to know what the pH is, because if it's warm weather and the pH is really high, the ammonium volatilization is much more rapid. But even in a compost sample, if you have the ammonium, you can get a little bit of an idea of how well cured that compost is. So ideally, a cured compost is going to have almost no ammonium left. There's a lot of compost samples I see that are just partially composted and still have 1,000 or 2,000 parts per million of ammonium. So it's not pure compost. So I would always ask for ammonium.
Great. Thanks, Christine.
Thank you, Christine.
Okay, I'm going to end this poll so we can keep moving along here. Oh, I should have brought that up. So here, I'll bring up my red thing. So we know that we have 1.3 kilograms per 1,000 liters, or if you want to think in pounds, and we know that we spring applied, so that's why I brought up this chart specifically compared to the fall. And we know that we had a 9.58% dry matter. So that means, and it's an immediate incorporation because it's injected. So that means we would retain about 95% of our ammonium nitrogen. So you would multiply that amount of nitrogen that we know we have by the 9.95%, giving us 1.24 kilograms per 1,000 liters of ammonium N, or 10.5 pounds per 1,000 gallons of ammonium N. So before we calculate step 2, knowing how much nitrogen we're going to get from our organic N, let's review what affects how much organic N becomes plant available. So estimating plant available N is from organic N, I'm saying N a lot, is not as straightforward as the ammonium nitrogen pool due to organic N needing to be mineralized by the soil microbes, as I mentioned earlier. So there are several factors at play, including your soil type and conditions, your manure type and composition, and this being a biologically driven process, it is variable in time and space, year to year, field to field, and even day to day. Therefore, predicting how much organic nitrogen will be mineralized each year can be tricky. Depending on the information that you have available to you, this fraction of nitrogen credits can be estimated in a few different ways. So this is probably the most simple out of the three that I'm going to show you, but this is simply based on the type of manure that you have, and it's just showing credits for available for the first year. Or you can base it on your soil type and dry matter content in combination, specifically your soil drainage. So here you can see that soggier soils result in less plant available nitrogen because soggy soils are more prone to denitrification, which loses money but also causes greenhouse gases. So you can see here 36 versus 20, and it's the same. 36 versus 24. Yeah. And so, for example, if a producer, so I think it was Susan Kelly, used Charlie McDonald's poultry manure at a rate of 4 tons per acre, so 1.55% of total nitrogen as is, that is 124 pounds of total N applied per acre. And on well-drained soil tilled in, that's 36 pounds of nitrogen mineralized per acre, but on poorly drained soil tilled in, that's 24.8 pounds of nitrogen mineralized per acre. So overall, that's 11.2 about pounds of nitrogen lost because of your poor drainage soils. And to kind of take that a little bit further and put a money sign in front of it, if urea is $1,400 per 2,200 pounds, so about $0.64 per pound, and since urea is 46% nitrogen, that's about $0.29 per pound nitrogen. Then overall, that's $3.25 per acre lost because of poor drainage. So the carbon to nitrogen ratio is also a good representation of the chemical composition of the manure to estimate organic nitrogen mineralization. The table here shows estimations of available nitrogen following application for years 1 to 3. Again, based on carbon to nitrogen ratio and application time. Like I mentioned earlier with the diagram of nitrogen pools in the soil. If you have a lot of carbon and not so much nitrogen in your manure, your nitrogen can be completely immobilized. So 2 things to note from these different values in the tables. Early season applications have greater nitrogen mineralization values because there's a longer period for decomposition to occur. And low nitrogen manures may cause net nitrogen immobilization in year of application. I just repeated myself. Which brings me now to the next step in our example. So determine the amount of organic nitrogen that will be plant available in the first year of planting or mineralized. So we know that we have 0.18% organic nitrogen in our manure. And because this is liquid manure, we're going to calculate that by volume, giving us 1.8 kilograms per 1,000 liters, or 15.3 pounds per 1,000 gallons. So to determine the amount of organic nitrogen that will be mineralized and plant available in year 1, again, you could do it for year 2 and year 3. We're just going to stick to year 1 for this specific example. You're going to multiply the volume by the appropriate percentage available shown in the table. Yeah, that's going to show the answer. Okay. So I'm going to bring up the poll here and you can take a shot at. So all information should be there for you to be able to answer that one. And I see we're hitting that 1:30 mark, so I'm not gonna give you a whole lot of time. Sorry to figure this one out, so I'm gonna keep moving along. But to answer this one, so we should have taken the amount of available or the amount of organic nitrogen in from that percentage and multiplied it by 0.2 because our carbon to nitrogen ratio was less than 15 and we were doing it for the first year, and we applied before June 15th. So now that we know how much nitrogen will be plant available in the liquid manure, how much nitrogen per hectare or acre is needed pre-plant? So we know that we need 115 kilograms per hectare of nitrogen, and we're going to be doing 50 kilograms per hectare side dressing. So for pre-plant, which is what we want to calculate, how much do we need? 65 kilograms per hectare of nitrogen or 58 pounds per acre. So that's the total amount of nitrogen that we're going to need for the 20 acre or 8.1 hectare field. And we know from previous calculations that we have 1.6, if we add the ammonium N and the mineralized N, we're going to have about 1.6 kilograms per 1,000 liters of N available, or if you like to think in pounds per 1,000 gallons, 13.6 pounds per 1,000 gallons of nitrogen available. So how much manure do we need per hectare or acre? And here we go. Did that poll come up? Okay. Okay, I would have liked to give you more time, but again, I've already gone over, so I'm not going to. So We know we need, for the total amount of area, we need 526.5 kilograms of nitrogen, and we know we have 1.6 kilograms per 1,000 liters of nitrogen. So that means we'd need about 329,000 liters per hectare, 1,000 hectares of manure needed, or thinking of pounds, we know we need 1,161 pounds of manure in total. And so we would divide that by the 13.6 pounds of per 1,000 gallons of nitrogen that we know, which would give us 85,368 gallons per acre of manure needed. So thanks everyone for your participation in those polls. So just to summarize, manure is a valuable nutrient resource that can help offset fertilizer costs. Nutrients from manure can be easily lost to the environment if proper management is neglected. And knowledge of how much manure you have and the nutrient composition through testing or book values, if that's not possible, are two great steps in developing a solid manure application plan. And thanks so much for listening, and I apologize for going over time.